For over a year now, I have been on a mission to try and turn algae into fuel and potentially other things. But can this green goo really power your car? Well, the answer is yes, but in order to understand how, we need to explore the science behind it. Algae are an ideal candidate for this, as they are a very potent carbon sink, many times more so than trees. Additionally, many species of algae can be grown almost anywhere, in oceans, in lakes and ponds, smaller, more rough and ready DIY cultures. I think you get the picture. Not to mention that they have the ideal chemical makeup for things like biodiesel and biodegradable polymers, due to things like their high lipid content, especially with strains like what I'm working with, Chlorella vulgaris. But why am I doing this? Why am I researching algae for these types of uses? Well, I am doing this because if I am able to produce fuels and other things from algae, something almost anyone can grow, then that means we have an abundant feedstock that anyone can use and access to become more self-sustaining for their energy, for their materials, and so on, and can thus become a tiny bit less reliant on the market system to provide those things for them. One of the main bottlenecks in what would be my algae to fuel process is the amount of time it takes to get the algae harvested out of its culture media, as well as how clean the algae is once harvested and dried. In the past, I have tried both gravity and vacuum filtration, but both ended up failing. Gravity filtration is impractically slow, and on attempting to do vacuum filtration on my algae, every time I tried it, it ended up blocking and clogging my filters. I may try vacuum filtration again in the future, but what I found to be the most reliable method at present is to simply passively sediment the algae in its container, followed by siphoning off the liquid phase. But what if I could do exactly this, but in a quicker and more efficient way? Well, that's what professional biologists have been doing for decades, using things called centrifuges. A centrifuge is a piece of equipment that spins very fast to exert outward force onto a substrate. But centrifugal force is actually kind of a misnomer. The actual mechanism by which this works is called centripetal force. Centripetal force is, in simple terms, the proportionate action of one object's perpendicular motion upon another. Think about it like this. When you go on a roller coaster that has loop-de-loops, at the loop, the cart wants to move outward as well as forward, but it can't move outward because the track forming the loop presses back against the cart for the duration of the loop. The faster the cart goes, the more perpendicular velocity it will have upon entering the loop-de-loop, and hence the more centripetal force the track will apply back to the cart. What this means in practical terms is if you spin something fast enough but bind it to an axis, you can effectively create artificial gravity, even greater than that of Earth's. This is the same principle behind those massive centrifuges that trainee astronauts climb into in order to test their ability to withstand elevated levels of gravity to determine whether they can safely enter space through rocket launch. So what does this mean for me? Well, centrifugation to me seems like a logical step in evolution from my current sedimentation process, except the increase in artificial effective gravity will make that a lot faster. Now, I could just go out and buy a centrifuge, but they can be a little bit pricey for my needs, and well, where's the fun in that? I think you can see where this is going. Welcome to this episode of Doing It Ourselves, where I design and 3D print my own centrifuge for harvesting algae. So let's get right into it. Also, stay to the end to find out if 3D printing your own centrifuge is cheaper than buying one. So as I explained earlier, centrifugal force can result in artificially elevated levels of gravity, and this is very useful for separating solids from liquids in a quick and clean manner. And now I'm going to demonstrate that principle. To do this, I filled a 50ml vial with a concentrated chlorella culture, capped it off, and tied a piece of string around the neck. What I'm doing here is creating a sling of sorts, which does a very similar thing to a centrifuge, just far less efficiently. For you anime lovers, this also appears in Dr. Stone. Anyway, I tested this outside because I didn't particularly want to clear up a potential mess of algae and broken glass. As you can see, before I did anything, the culture in the vial is a homogeneous, uniform mixture. After many minutes of reluctantly spinning the vial sling, the culture started to show some minor sedimentation. This can be seen when we face the vial at the sun, which reveals a lighter layer at the top of the culture starting to form. However, this is only a demo, and it kind of sucks for actual use, as it's impractical, dangerous, and highly inefficient. And this is where my idea for a 3D printed centrifuge comes into play. For ease of design and assembly, the centrifuge is going to be hand cranked. The problem is that for centrifuges to work effectively, they need to operate at decently high speeds in order to ensure good separation of their substrates. To overcome this hurdle, I'm relying on the principle of gear ratio. Yes, this is the first time on this channel, or ever in fact, that I am 3D printing gears. The idea is that by using larger gears to drive a smaller pinion gear printed into the spindle, I can push for higher speeds with fewer hand crank rotations. In principle, I could just print a few simple involute gears, with each gear scaling between the hand crank and spindle. However, this is inefficient in terms of both material and space used. Scaling gear ratio this way is kind of suboptimal. Additionally, I would have to design different parts for each gear stage, and like a lot of good engineers, I can be fairly lazy. Enter compound gears. Unlike simple gears with only one toothed interface, compound gears are a combination of a larger and smaller gear stacked on top of each other, both sharing an axis. What this enables you to do is rotate the whole compound gear assembly as if you were just engaging the smaller gear. Now I needed to design a base that I could attach the transmission gear train and the other parts to. Initially, I thought of merely printing a base with fixed posts for the transmission gears. The problem with this idea is that I would need to reprint the whole entire base if I got the positioning wrong and needed to iterate. Therefore, I designed a base with adjustable posts that slide on a rail. What this allows me to do is adjust the fit for the transmission gears on the fly and subsequently minimize waste from reprinting the base. I intend to continue using the aforementioned 50ml vials to process my algae with this centrifuge. Hence, I printed sleeves for them. These parts have a hole in them that allows them to be fastened to a central hub which sits on the spindle shaft. The shaft has a D-section that the centrifuge hub neatly slips onto, and this is how torque will be applied to the hub. The posts for the transmission gears have a small hole in them, which is for receiving a cap to ensure the gear remains on the post. The posts themselves are secured in place by a horizontal nut and bolt combo. However, later on you will see why this design and the design of the centrifuge more broadly is flawed, and why I needed to completely overhaul the entire thing. Anyway, to make sure the gears I put together in FreeCAD fitted correctly, I printed a rough mock version of one of the transmission gears and tested it out. The tolerance is slightly off, it's a bit too snug on the post, and the gear itself is too tall to fit. However, it meshes with the spindle gear just fine. All this means is the gears needed to be printed at a reduced height, and tolerance is adjusted for a slightly looser fit. As for the drive gear, all I needed to do is take my existing gear profile, attach a post to it, and design a socket and lever to hold onto when turning. However, as I got further into assembling and testing the transmission assembly, I began to notice some fundamental problems that eventually led to me abandoning this design. To preface, the spindle gear of this design has 16 teeth, and the gear it's meshing with has 64 teeth. That's a 1:4 ratio. The smaller gear of the compound gear I had initially designed had 15 teeth. This meant that any identical gears at each stage would also be making roughly a 1-to-4 step in gear ratio. When you scale gear ratio like this, no matter the design, every additional gear stage is going to require exponentially more torque in order to rotate the spindle at the other end. In the case of my initial design, the first gear in the train turned the spindle fine, but when I tried to do the same via the second stage, it proved far more difficult. I tried bumping down the gear ratio a bit. I thought that perhaps the step-in ratio of meshing 15 and 64 tooth gears may have been a bit too steep. So the first thing I did was tweak the compound gear a bit so that the inner gear of the compound had 24 teeth instead of 15, in order to slightly lessen the step in gear ratio. This improved things slightly, and I was actually able to get the spindle to rotate a bit. However, this was still far from being viable for practical use. But the gear ratio wasn't the only problem, or even the main one. The primary culprit here is the base itself. On top of being very hard to print due to having rather extensive bridging and thus requiring a lot of hard to remove support, the structure of the rail that the gear posts sit on was rather flimsy, and installing the gear posts securely only marginally improved rigidity. This resulted in a rather flexy gear train with inconsistent meshing, and gear posts that after a few turns of the gears sitting on them would shift slightly, thus rendering what would be the whole system very unreliable. On top of that, I was relying on printed threads for the hub, which proved too loose to be safe. So I had a good think, and even tried to recover things by designing and printing parts that would make the transmission more rigid, such as this bracket. These would sit between gear posts and ensure the rail had fewer degrees of freedom. But in the end, I ended up coming to the conclusion that I was ultimately just tacking on fixes to a broken system and adding unnecessary complexity, which would be avoided if I had just started from scratch and completely overhauled the design. So that's exactly what I did. I soon got to work redesigning pretty much everything about the centrifuge. So back to grinding hours in FreeCAD it was. With this, I had a few goals in mind: to make things more rigid and sturdy, to reduce friction, to make things safer, and to compensate for PLA's relative weakness when it comes to moving parts, especially at the speeds needed for centrifugation. First off, let's talk about the base. The most obvious change is how I made the base a two-part design. This makes it easier to print, especially on smaller machines. The spindle end of the base now has a slot for a 10mm bearing, as opposed to relying purely on a plastic bushing to hold the spindle, as with the previous design. This not only strengthens the part, but also with using a bearing, it's also going to reduce friction quite a bit, especially with the right lubricant. The bearing I'm going to be using is just a standard 10mm ball bearing, with the stock grease replaced by a slightly diluted silicone-based PTFE grease. I am diluting it slightly with isopropanol to make it less tacky and more slick. The other half of the base has also changed dramatically in order to solve the flimsiness issue. The new rail has a more robust design, where two screws and nuts hold an adjustable sled in place that rests neatly within the chamfers of two channels. The sled has a square lip with a hole in it that the corresponding gear posts can slot onto and be fastened to the sled. The bottom of the sled has a countersink so that the screw heads don't protrude and throw off the positioning of the gears. Onto the hub now. Firstly, the slot profile of the spindle shaft has been altered to accommodate the redesign of that part. It now looks a lot closer to an industry standard D-slot profile, and this should decrease wobble, which was a problem with the previous design. The other significant change is the addition of 4 slots for 5mm nuts, and this means that the sleeves for the vials will have a much stronger grip on the hub and stay in place, and obviously this makes the whole system a lot safer by reducing the likelihood of the sleeves unfastening themselves and flying off at 1,000,000 miles an hour in an unpredictable direction. And this brings me to the spindle shaft itself. This has been completely overhauled, even though it may look slightly similar to the old design. At the bottom it has a 10mm section that slots into the corresponding bearing, and this is fastened to the bearing from the other end with a washer that I've designed and an M6 bolt. However, that's not the only reason for making the centre of the shaft hollow. You see, PLA, while decently strong, has a tendency to snap or shatter at break rather than bend, and it also tends to deform under continuous load. To compensate for this, and this applies to the gear posts of the transmission as well, I decided to use internal bolts as a kind of reinforcement that can bear most of the mechanical load instead of the PLA. The beauty of doing things this way is that you can print almost any shaft topography you need while having the part be almost as strong as something machined in metal, because, well, part of it is. The easiest way to do this would be to print your sleeve and insert a threaded rod into it to serve as the core structure. But all I have on hand are bolts, and so that's what I'm using for this purpose. The strength of the spindle is crucial here, as it's going to potentially be reaching RPMs in the 4-digit range, which would be dangerous to do if I relied solely on the strength of the 3D print itself. The next important thing to talk about are the gears. That is the gear on the spindle and the discrete gears themselves. Gears have a property called module. This isn't something you can tangibly measure with a ruler, but is a property integral to the topography of a gear. It's typically measured in millimeters and is calculated by dividing the diameter of the pitch circle by the number of teeth. Here is a gear I printed for my initial centrifuge design. It has a module of 1mm and 64 teeth. Here is its replacement. This gear has a module of 0.6 and has 106 teeth. As you can probably guess, a higher module means fewer larger teeth, and vice versa. Coarser gears are very good for when you need a lot of torque and you need very strong teeth that can handle high load, whereas finer modules tend to be better for high-speed applications, due to more consistent meshing resulting in smoother operation. I have opted for the latter, as my centrifuge is going to be running at decently high speed and requires very consistent motion for effective centrifugation. Now that that's out of the way, back to the video. Other changes to the gears include the addition of cavities in order to reduce facial contact and save material, as well as the fine-tuning of gear size to ensure best fit. The gear posts have increased height, are slimmer than the original design, and have spacers to reduce drift and play. The socket and lever are compatible with the improved centrifuge design and so do not need to be redesigned or reprinted. Finally, I've completely redesigned the vial holder. It's now a top-loaded design with a cap on a hinge, and the bottom piece is printed horizontally. This is important because centrifugal force may lead to the vial ripping a vertically printed design in half while spinning at multiple thousand RPMs, which obviously is not ideal, hence the changes to the design. The overhauled design is also less bulky, which puts less strain on the spindle. After a few small tweaks and dialing in of tolerances, it was finally time to begin assembling the centrifuge. So without further ado, let's put this thing together and give it a test. Cue the obligatory royalty-free rock music. So there you have it. We have successfully built a centrifuge that can effectively sediment algae from its medium. Now obviously the centrifugation in the test was incomplete, as this was just a short test run. I didn't run it for a long time. It's just a proof of concept. The centrifuge itself is also still not perfect. It still wobbles and skips a little, and this needs to be improved. But as I said, this is only a proof of concept, but it's one that, because of 3D printing, I will be able to iterate upon relatively easily. When it comes to centrifuges, there is a fair bit of complex maths involved, but for now, let's just go over some of the basic stuff. The spindle gear has 40 teeth. Remember, I reduced the module, which means we have more teeth. That's why the spindle gear has so many teeth. Then each of the compound gears, let's just label them comp, each of these have 106 outer teeth and 34 inner teeth. For the simple gears, they each have 106 teeth, because they are simply just a slightly iterated version of the compound gear. And finally, the drive gear has 134 teeth. And now we have these numbers, we can finally calculate the gear ratio of the centrifuge. The way we do this is we iteratively, at each stage, take the number of teeth on one gear, and we take the teeth of the gear it's meshing with, and we divide the number of teeth of the larger gear by the number of teeth of the smaller gear to give us the gear ratio at that stage of the gear train. So in this case, the first thing we need to do is we need to take the number of teeth of the first compound gear in the gear train, that's 106, and we need to divide that by the number of teeth on the spindle, which is 40. 106 divided by 40 is 2.65. Now we need to move on to the second stage, which is the smaller gear of one of the compound gears meshing with the larger gear of the next compound gear. So we need to divide 106 by 34. And this gives us around 3.1. And remember, we're doing this twice, because we have two of the same compound gear in the train, and also because the simple gear also has 106 teeth. Next, we're going to calculate the gear ratio between the drive gear and the simple gear in the gear train. It is the last stage of the gear train, and that is 134. That's the number of gears on the drive gear, and we divide that by 106. And that gives us 1.26 or thereabouts. So essentially what we have is we have a 2.65, we have a 3.1, we have another 3.1, and we have a 1.26. And now all we need to do to get the final gear ratio of the gear train for the centrifuge, all we need to do is we need to multiply these together. And when we multiply all these together, that gives us our final value of 32.13. And what this means is our final gear ratio is roughly 1 to 32. What that means is that for every one rotation of the drive gear, the spindle will rotate roughly 32 times. If I was to rotate the drive gear 10 times in a minute, that would result in 320 RPM. There's all kinds of formulas you can use to convert RPM to effective gravity, But I won't get into that. That will be something for a separate video. Last but not least, one thing I wanted to touch upon was the cost of building this centrifuge. A kilo of overture PLA, which is what I've been using throughout this project, costs about 12 to 13 quid, or about $17 American. The bolts I used for the spindle cost me about £10, and I received 20 of them, meaning the bolts cost about 50p each. Now, the amount of filament used for each component will differ a lot depending on your slicer settings. But what I can tell you is that throughout this project, even with trial and error, failures, reprints, etc., I never had to open a brand new spool of filament. So now let's do some guesswork. I used 2 different colours for the centrifuge, so let's say you order 2 1 kilogram spools of filament, 2 spools of PLA. Other materials may cost a bit more. And then you take into account bolts and fastenings and so on, so say about £20 for all of those. This brings us to a total of about £46, but that's a very pessimistic number. It's likely to be around half that. So if we only factor in materials, we can safely say that you can build my centrifuge for under 50 quid. Now, to put that into perspective, if you take a look online, you will see that commercial centrifuges can be up to 5 times that price. And on top of that, they also have a smaller volume. Now, yes, there are cheaper options available, I'm not denying that, but they still have lower capacity and aren't nearly as modular as my design. Anyway, thank you all very much for watching. It's great to be back. All STLs will, as always, be freely available on my Thingiverse page for you to download, tinker with, and improve. Take care, and I will see you all in the next video. Bye for now.